Yeah. So I'm writing a book at the moment. It's got the title When the Uncertainty Principle Goes Up to 11, and it's all about the deep and fundamental links that exist between quantum physics and heavy metal, and indeed all forms of metal music. Death, thrash, black, stoner, hair, whichever type, whichever's your favourite subgenre of all of those. We'll be covering all of those. Let me read you a little bit from the blurb that might feature on the back of the book. It's certainly the blurb that I initially submitted with the book proposal. It'll give you an idea what it's all about. There are deep and fascinating links between heavy metal and quantum physics. No, there are, really. You'll find out how the Heisenberg uncertainty principle comes into play every time a guitar chugs or a cymbal is choked. Learn why the patterns on a drumhead are exactly the same as those formed by electrons in quantum corrals, and discover how it is that metalheads in mosh pits behave just like molecules in a gas. In other words, when the uncertainty principle will show you how a remarkably large amount of the physics underpinning the quantum world, despite the weirdness for which it's so renowned, is at play every time your favourite band takes the stage. So, as well as the book, we're going to have an enhanced version of the book, which is going to include videos, and we're going to embed those videos in the ebook. And the book is also being illustrated by a guy called Pete McParlin. Some of you who might be familiar with Brady Haran's channels will have seen Pete's work. It's just fantastic. It makes a huge difference to the book. Every time I get some new illustrations from Pete, it's like, oh, really excited. He does such a good job in translating what's rather garbled in my brain into a nice, easy to understand illustration diagram. And he's got a real quirkiness about it. So this is going to be a taster of the types of video that we're going to embed within the ebook. Before introducing the concept of waves on strings and the concept of waves in guitar strings and how that couples into what's happening right at the quantum level, I wanted to introduce waves much more generally and much more fundamentally. And so what I really wanted to do is to look at just the fundamental origin of a sine wave. Where does the sine come from? You'll have heard of sines before when it comes to trigonometry and angles, but then when we have a sine wave, how is that coupled directly into the sine of an angle? Where does that come from? Why do we call it a sine wave? Why is it a sine wave? So let's look at the mathematics of circle pits. So here we have a pit, and we have a marsher. Let's call her Marcia, dashing around the outside of the pit in a admittedly fairly unusual perfect circle. So her starting position here will be 0 degrees, and she'll dash round to here, 90 degrees, then dash round 180 degrees, 270 degrees. So if we run that as a little animation, it looks like this. And she's following the circle round. Okay, so fairly straightforward, perfect circle, moving around through 360 degrees each time she runs round the circle. How does that have anything to do with sines? Well, let's just think about this a bit more carefully. So Marcia starts off again at 0 degrees. Let's have her run this time, not the whole way around, but let's have her run through up to 45 degrees. So she gets there. So that's a 45 degree angle. And what we also note is that we can make a measurement of how far she's moved in the X direction and how far she's moved in the Y direction. So here she's got no movement at all in the Y direction, but in the X direction, well, she's got the radius of she's out from the centre of the circle by the radius of the circle. Here she's moved round. Now she's moved in a little bit in X, but moved up considerably in y. And so she's what we call subtended an angle, and that angle is theta. The sine of this angle is the opposite over the hypotenuse. So this is a right angle triangle. Here's the hypotenuse, and here's the opposite side to where that angle is. Now, importantly, what we can do is we can just set this, say this is a unit circle. That means we can say that this is 1 meter, for example. Okay, they'd have to be extremely small marshers, but maybe they are. Maybe it's sort of like a Lilliputian or circle pit. But let's just say, for sake of argument, that from here to here, the radius of the circle pit, or the radius of the circle around which Marcia is dashing, is 1 meter. That means that the sine of the angle is this length divided by 1. And as you know, any number divided by 1 gives you that number. So what this represents, as Marcia dashes around, it's certainly the sine of the angle, but if we make this equal to 1, then what it actually is how far she's moved up in the y direction. Now we could use another function, something called a cosine, to get how far she's moved in the x direction. And here's how that sine function varies as you go right across the circle. Here's Marcia's current position, which is 45 degrees, midway between 0 and 90 degrees. So this is where she is in terms of the sine function. So this length in y, in the y direction, is represented by the position of this dot. If she runs round to 90 degrees, you see it's 1, which is what we'd expect, because if she's here, then in terms of the y direction, in terms of the y distance, this has got to be 1 because it's a radius. Once she gets to this point, she's 1 radius away from the centre in the y direction, so it's got to be 1. And then she moves around, comes around to 180 degrees. How far is she now in the y direction? Well, she's back to 0 again, which is why we've got 0 here. Moves around to 270 degrees, which is the opposite of here. So here we've got, let's call this the 0 line. Above the 0 line, positive values. Below the 0 line, negative values. So here, she'd have 1. The other side, she is -1. So it's symmetric, and all that's changed is the sign. And then she dashes round and gets back to 0, and the whole thing repeats. Okay, let's hammer that point home. So here's Marcia. She's at that 0 degree position again, 0 degrees angular displacement, as we call it. This red dot's going to represent her position in terms of the sine of the angle as she moves around. So she moves from 0 to 45, etc., etc. So she's going to do this quite slowly this time so you can just follow it through. So she's coming round, gets to 45 degrees as before, now coming up to 90 degrees. Sine function is 1, moving through, coming to 180 degrees, getting ever closer to that line. So 0 now, back round again. Now she's into negative numbers because she's on the other side of this dividing line. Now she's coming up again, and she's going to repeat the entire cycle, get to 0, and then continue, etc. Let's just speed that up a little bit, see what it looks like. You get the idea. What's absolutely remarkable, let's stop Marcia running before she gets too dizzy. What's absolutely remarkable, and I'll be focusing on this a great deal, a huge amount in the book, is that this function, this relatively innocuous looking function, the sine function, crops up time and time and time and time and time again right across physics from every possible type of problem. At some level, this sine function is going to feature. And in fact, the true genius of a man called Fourier, who we're going to look at his work in quite some depth in the book, is that he worked out that you can make up any pattern, any function. Okay, not every pattern and not every function. Mathematicians might get a bit irked at me when I say that. But the vast majority of interesting patterns and interesting functions, you can make any of those patterns, any of those functions, just by adding up sine waves of different heights, which we call the amplitude, different frequencies, which is the rate at which it repeats, and different phases, which is how we move it along the x-axis. By mixing up all those different sine waves, you can produce pretty well whatever function, whatever pattern you like. Now, as I've said, the book is of course going to focus on guitars because they're absolutely central to metal music, but so too are drums. And in fact, if we look at the motion, at the dynamics of the bass drum beater, which you could argue is pretty important in a great deal of heavy metal, we're going to do a simple experiment to measure the dynamics of a bass drum beater, and what we're going to see is that the sine function falls out yet again. Despite the fact that we're not talking about Marshers now or a circle pit, we're talking about a very, very different system, and yet the same mathematics describes it. And the way we're going to measure the motion of the bass drum beater is, well, you can see in the end here, I hope, let me see if I can get that right, you can see in the end we've got a mirror. And what I'm going to do is I'm going to bounce a laser, just a laser beam from a simple laser pointer, off the end of this. And by tracking what the laser does, we've got a very accurate way of tracking the motion of the drum beater. So at the moment, you just have to take my word for it that the laser beam is going from here, hitting a mirror here, and then ending up on the wall over there. The problem is there's nothing at the moment there that will scatter the laser light to our eyes. So we can see the laser beam when we put something in the way, and that light is reflected, scattered into our eyes. But without it in the way, we just don't see anything. So it would be really neat to be able to see the laser light path, so we can see it at different points. But it would be good and quite cool, really, to be able to see that laser beam. You've seen laser beams at many rock gigs, I'm sure, where they're snaking off in this otherworldly fashion. At the moment, we can see it at points when we do that, but if we want to see the beam, then we need something in the path of the beam that will scatter the light, the laser light, into our eyes. So what can we use to scatter that light into our eyes? Well, luckily I work in a physics department. I can just go and get some liquid nitrogen. Now, at the moment you obviously can't see the laser beam, but we can visualize that laser beam by using a little bit of liquid nitrogen. So we bring the liquid nitrogen in, and hopefully you can start to see that laser beam appearing. So tracking it from back here, from the laser pointer all the way through, all the way down to the drum beater, and then it's bouncing off the drum beater and following its merry way off to hit the wall. And by moving the drum beater up and down, we of course change the path of the light beam, of the laser beam. Path of the laser coming in and the outgoing path, you can see it bouncing off the mirror down here, and you can see the two laser beams coming out. To analyse the motion of the drum beater, there's a fantastic program I found online. It's called Tracker. As you can see, it's part of the open source physics written by Douglas Brown. This is just a really wonderful piece of code. And what you can do is, well, I'll open up the video of the drum spot. Okay, so here's our video. And you can see as before, the spot merrily bouncing up and down as the drum beater moves back and forth. Great thing about this program, though, let's move that right back to the start, is we can just track new. So we're going to just treat it as a point, because it's a bit of a blob, but we can treat it as a point. And now what we can do, which is quite neat, is we can mark the position of that blob, and as we do that, let me just change that to Y. What we'll see is the Y position, and we can map that out as a function of time. So let's do that. And you can probably guess what type of graph we're going to get. I'll try and do the center of mass of these points. And now, I hope you can see already, we've got something that's a pretty good sine function. Now, we could just leave it there, but what I want to do is just continue on tracking this, because there's a bit of a difference between this and the circle pit. In that, with the circle pit, if we assume that Marsher the mosher just keeps running round and round and round and never loses energy, then everything's fine and that sine continually repeats. In this case, however, it's absolutely clear that the beater is losing energy because it comes to a stop. The drum beater comes to a stop at some point. And so we should be able to see that as we continue to plot out the motion of the beater. So let's keep doing that. Let's add a few more points onto this. Okay, so there's our how the drum beater behaves. And in this case, as you can see, it's got that characteristic sine wave shape, but it's decaying off. And that's decaying off because the drum beater's losing energy. What we're seeing here in front of us on the screen is effectively a representation of the uncertainty principle, but with a drum beater. And similarly, every time a metal guitarist chugs away on a particularly heavy riff, damps the guitar strings to get that crunch that we all know and love so well, uncertainty principle in action. But you're just going to have to wait for future videos and for the book to see just why that is the case.